even with an arbitrary n iterations. And I can then determine the normalized unimodular multiplier, its inverse. And from that point on, I can get the generating invariance and get the associated rewrite rules simply because it's a very mechanical process. And then I can certainly find the Hermite normal form of the matrix A joined with minus P. That's easy enough to do. I can know what operations are. So I can do this for a general n, not just for n equals to 3 or 5 or something like that. I can do it for a few other things. For example, actions which basically take my diagonal action, which takes one of the generators and multiplies every exponent by the integer mod n, and then other ones sort of do this sort of cyclic type process. And again, I can figure out the unimodular multiplier, its inverse. I can figure out the generating invariance, associated rewrite rule, in a general way. So that turns out to be convenient. Okay, so just in case, so it doesn't need to be a group of order 5, 17 or something like that. I can do it in sort of things. I can take a system of n equations and these n unknowns, and I can mess around with them and reduce them in a very mechanical way. So I can kind of create a procedure to do this. Okay, does that make sense? Okay. And so what I've done so far is I've sort of said, look, this is how you, if you start off with finite abelian group action, I can transform the variables. So it's a diagonal action. I can take diagonal action and play with the exponents. So I can generate the invariance without a lot of work. And I can generate, I can rewrite things in terms of these invariants. And so I've got that process. And it requires a tool no more complicated than integer linear algebra, Hermite normal form. I just say it's a commonplace tool that can be taught in the second or third year of undergraduate program. Okay. Now, how about solving polynomial systems? Let me talk a little bit about that. I think I have a little bit of time left. And so I'll show you how to use invariance and rewrite rules. I'll talk about something called AP degree and AP homogeneous, and solving invariance systems. I'll just sort of run a little example through there. And so the example I'm going to use is an example that we took from a SIAM numerical analysis book, or a journal paper, steady state for neural network model. And so we got 3 equations, 3 unknowns. It's actually an equation that was used in Karen Gauderman's paper. 3 equations, 3 unknowns. This is invariant under permutation. X1, X2, X3, again, same permutation we saw at the beginning of the lecture thing. However, it's a little different. It's not contrived. And what's different about it is the fact that no single polynomial is invariant in the permutation. The solution space is invariant, but not each individual. So that's a little different. Okay. So what do you do in those cases? You can't just sort of take each equation and rewrite. You just can't find the invariance. Rewrite each equation in terms of the invariance and away you go. That just doesn't work because each equation is not invariant, just the system is invariant. So that's a little different. Okay, so what you do in this case is that we're going to define something called AP degree. Okay, and what it's going to do is it's going to take, go ahead please.
Do you go back on to the original system for a moment? Is it just invariant under this 3-way permutation, or is it also actually invariant under the whole, under any permutation of the 3 ways?
It's invariant under any. So that's a good point, which so in fact, this is the point I was going to make, that here's a system which is actually invariant under the whole group, okay? But I can only deal with the cyclic subgroup because the whole group is not abelian, but the whole group is S3, right? I can only do with the cyclic subgroup. Okay. So I can't do with the solvable. So what happens is that I can look at any monomial, and I've been looking always for when is a monomial, when can I take apply this matrix A mod P, and when can I get it to be 0? Well, there's other, so that's good, then it's invariant, but there's other options. Sometimes it's 1, sometimes it's 2, all the way up to whatever the order is. And so whatever those numbers are, I'm going to say it's either invariant or homogeneous of degree 1. Invariant would be homogeneous of degree 0, but I can also have homogeneous of degree 1, 2, 3, 4, etc. Which it just says, take my matrix of exponents, apply it to my exponents. If I get 0 mod p, that's great, then it's invariant. Otherwise, maybe I get 1 or 2 or 3, because I can order the groups also from 0 to p minus 1, where p is the size of the group. Okay, and furthermore, I can take, that means that any polynomial I can actually write as a sum of things that are sort of, well, this one's of invariant, this one's of order 1, order 2, order 3, or order minus 1, etc. Right? Okay, and each term is called homogeneous of degree, of AP degree D. So this actually comes from Fougere and Fougere's paper, and Fougere and Schwartz's paper. And so it turns out that, of course, something's of AP degree D, if and only if it's like the standard homogeneous type equation. So if you plug in, rescale, and you can pull out a certain exponent, then it's homogeneous of degree D, AP homogeneous of degree D. Because every term has this common term. Okay.
So let me just parse this. Lambda is a complex number, G is an integer.
Lambda is the set of is an expression which is sort of a combination of the generators of the finite abelian group. Right? Remember the alpha and the beta to various exponents.
Sorry, I'm
Okay.
just.
So lambda would come from the finite group.
So then what's the answer to the
So the quantity on the right side of the equal sign,
Okay.
the whole quantity,
Yeah.
is a polynomial over k, right?
What is the
An
meaning?
irrational function over k, sorry.
What is the meaning?
No,
of
it depends on the
D?
D.
Yeah, what is the meaning? Well, so here's what you do. Okay, so no, it's not true. It's not so true.
And alpha, beta, gamma are matrices.
No, alpha, beta, and gamma are just, no, you just think of them as alpha comes from Z4, or Z5, beta comes from Z7, and gamma comes from Z11. Okay, so now you take your exponents, and the exponents could be 0, 0, 0, and so we'll just call that 0. The exponents could be 1, 0, 0, we'll just call that 1. Or 1, 1, 0, we'll just call that 2. Some sort of enumeration that goes from 0 to the group order. But in terms of, but each number is going to correspond to the exponents, a particular set of exponents to the generators.
Okay,
so
I don't understand it all.
What I mean, so let's do the simplest thing. If I had alpha, Z2, and Z3, so I got two generators, alpha, beta, so the possibilities are alpha 0, beta 0, alpha 1, beta 1,
Isn't it
alpha
introducing the
0, beta 1. Maybe it's obvious.
Yes.
Zero. How many other variations are there? Alpha 0, beta 2, alpha 1, beta 2. Okay, so let's just call this 0, 1, 2, 3, 4, 5. So I'm going to number the group. This is a Abelian group. This is a group of order 6.
Okay.
And if the exponents kind of, if I apply A and I get sort of exponents like this, then I'm going to say it's homogeneous. If it's like this, I'm going to say it's homogeneous of degree 1. Like this, homogeneous of degree 2, homogeneous of degree 3, etc. So it's a little confusing, I admit.
What does lambda to the d mean then?
So lambda, lambda is sort of alpha, beta, gamma. Okay, so I'm going to take any, this lambda is going to be any element of this group.
All right.
Okay.
So.
And I'm going to apply A to that lambda. Okay. And it's going to change these exponents in mod P, and it's going to produce something alpha to that. I'll call it, what would be a good choice? D.
No, you already have a D. No, you already have a D.
F. Okay. Already have it. Right.
Yeah.
EF.
ABC.
I've got ABC. Yes.
A tilde,
No, actually,
A tilde, B tilde, C tilde?
A bar, B bar,
Yeah.
C bar. Okay, how's that? Okay. Okay, so now I'm going to take something, and so then I'm going to factor this out. I have to be lucky.
Okay, so D is a tuple.
D is a tuple, exactly.
So you really shouldn't be thinking of D as 0 through 5. D is really 0, 0, 0, 1, 1, 1,
Right,
0,
exactly.
1,
But
1,
on the other hand, I don't want to say something is a homogeneous of degree 0, 1, or
Well,
some
that,
isomorphism between the groups, right? Between the group and the, at least in terms of how you index things. Isomorphism is a bad word, I guess.
No, but actually the A dot U doesn't mean that every distinct element of the group would have a different degree.
Don't forget doing mod P. So it should have it should be either 0.
But you're taking linear combinations.
No, because we're working on monomials. We're working on monomials.
Yeah, I
so
know.
then,
So
okay, so
you-
if the 0 through 5 really should correspond to elements of Z6, then you want to order, you want to name them differently.
Yeah, of course. I mean, I'm just sort of sitting on the blackboard, just kind of going, okay, well, look, I can do something to try and give you that.
Okay. So what you're saying is that D is the representation of this tuple in
some ordered form.
in the group where you think about the group as now Z mod 6Z.
I'm just saying, yeah, I could think of it that way. But not, you don't necessarily think of it that way.
And I guess if
Just in some order.
if 2 and 3 were replaced by numbers that weren't relatively prime, then you really need to think about pairs and not singletons. Okay.
Yeah, so this may not be the clearest, I admit, and I apologize for not being clear. But okay. There is a theorem that says the following. If I take my set of, if I take a polynomial, rational polynomial in Z and Z minus 1, and I break it down into the homogeneous components, and then a set of toric zeros is sort of basically, toric means that none of the components are 0. So typically what we're looking for is all of the solutions where all the variables are non-zero. Okay. Then a set of toric zeros of F, all the non-zero solutions of F, is invariant by a diagonal action of the group. It is equal to all the toric zeros of all the individual components. I can describe why easy enough, because all I do is basically sort of say, look, any rational function can be any rational function can be broken down into its homogeneous components. The number of homogeneous components equals to the size of the group, and then I can sort of set up a square system of equations, like a van der Waals-like system. And something is 0 if and only if the homogeneous part is 0, basically.
What is U?
U is the representation of the group.
Okay, so it's just like G.
So it's just like G. That's right. Maybe this is a sort of a case where an example might be a little bit handier. Okay, and again, neural network example. Its zeros are invariant under this permutation, 3, 2, 1. Diagonal action, the exponents are going to be 1, 2, 0. The order is going to be 3. And I'm going to change the coordinates. And so here's going to be my 3 equations, f0, f1, f2. It turns out that I can break those down into 3 other. I can break down f0 into a sum of 3 components. This one of homogeneous of degree 0, so it's invariant. This one of homogeneous of degree 1. This one of homogeneous of degree 2. And it's easy to see. I mean, I apply a to this exponent, and I get a to the exponent 1, 0, 0. And in fact, I have an exponent 1 left. Here I have 4 and, or I have 2 and 2, mod 3 is 1 left over. Here I have 4 and 0, so I have 1 left over every time. Here I would have 2 left over every time. I would apply this, I would have the exponent 2. I would apply this, I have the exponent 1, and the exponent 4, so 5 and all, mod 3 is 2. Exponent 4, exponent 0, exponent 2, exponent 0, so it's exponent 2. Everything here is homogeneous of degree 0, degree 1, degree 2. Computation-wise, it works pretty well. So it says that when I change these, so now my system of equations, which was f0, f1, f2, is broken down into the homogeneous components. And it turns out that now I can look at these 3. I can break so now the solution is basically to solve those equations. It's the same as solving these equations, but these aren't necessarily homogeneous, or these aren't necessarily invariant. Okay, so that's not quite what I want, but that's fine. I can make them invariant by localizing. So I can sort of say, look. This is invariant, and this is 1 too many exponents. So let me divide by z1, and in fact, I'll make it every term invariant, because I'll take one of the powers away. Here I'll divide by z1 squared, and I'll take 2 of the powers away. And now I've got something which is invariant, 3 things which are invariant. But now I'm localizing at z1 not equal to 0. So now I have to be careful. Okay, so I do that. Look at that system. These are all invariant. In this case, I can rewrite. I can do my invariants. I can rewrite them in terms of the invariants. I've got 3 invariants. Again, I don't have polynomial systems, but I have rational systems. And now I've got y1. I have to worry about not being equal to 0. So that is a little more complicated. Turns out the system has 6 zeros, sort of a union of these 2 triangular sets. Okay. And so that's fine. I solve them. I get 2 zeros here and 4 zeros from this triangular set. So now I've got 6 solutions, all sort of with z1 not equal to 0, or y1 not equal to 0, I see. So the original system has 6 orbits and there's 18 solutions, where z1 is now, again, that combination of the original x's, not equal to 0. And so now I can work backwards because I've got my triangular representation of the z's in terms of the y's. And so I can now put them in terms, I can take solutions from y and put them, or z's, and put them in terms of solutions of y, which then in turn I can do in solutions in terms of x. And I can get 18 solutions in terms of x, and this system basically has 6 orbits. And then I have to worry about when z1 is 0, and then I write the system of equations. It turns out I get 3 solutions, and so I just find the solutions. Total number at the end of the day is 21. So I've taken my system of equations, I've broken it down. They're invariant. I've broken it down into sort of modulo of that particular group. And I've solved them. And then sort of problem is that now I have to sort of localize at a certain point. So I go back and forth. And then I have to sort of deal with the localization, which I guess when you solve polynomial equations, you always have that issue, and it's always a pain. So Fourier is the expert on this, and he sort of said, yes, you know, it's the pain that you have to deal with. Okay, so but it works. It's very effective. Not too much trouble. And uses very simple tools. But you have to take the point of view that the original system had a certain number of solutions. You put it in terms of invariance. Somehow you have to believe that the system is easier because there's less solutions. You know there's sort of, if you start off with 18 non-zero solutions, and now you're looking at a system with 6 non-zero solutions, that system with 6 non-zero solutions must be simpler. So, but it didn't look simpler, but it must somehow be simpler because you're looking for a system that has less solutions. And then, but so the building of this system is not so difficult. The solving the system must be easier. At least that's the assumption I think we have to work on. And then going backwards, because you've got a triangular system, is not difficult at all. So you can do this. And you always have this triangular system, right? Because of the Hermite form of the exponents. Okay. Given time-wise, do you really want me to do groups of homogeneity? It's
Well,
okay.
can I ask a question first?
Go ahead. Yeah, by all means.
So, the overall goal of putting together this algorithm is to solve the original system. With
The overall goal here is to find rational invariants, and then I wanted to give a reason why you'd want to do that, and that was to solve the polynomial system equations. And then, so the object there is to take your polynomial system equations. If you can sort of recognize that there's some symmetries, and the symmetries are some action, and you can sort of if the action is finite abelian, then good. Find the invariance, reduce the system to the invariance, and solve the invariant system, which is like working mod.
Sure.
Something, okay? And then working backward. And working backwards is easy.
So this is something that's going to work. It's only going to be useful if you have at the beginning a human recognizing that there is a system of symmetries.
Yes, that's exactly it. However, you don't need a human. Okay. So that's right. No, it's very, very smart. I mean, but it's not so unusual that a human will kind of go, look, here's the system of equations. But look, it's there is, you can see, but what you and I can see is with 3 variables is not so clear with 17 variables, right? So there's.
So what you're saying is that you can send a computer hunting for polynomial systems that this method is applicable to, but it's still going to be a very small fraction thereof.
Sure, that would make sense.
So one of these test problems for Grover bases that are hard are these systems with symmetry.
Okay. And the reason is because Grosvenor basis sort of takes the symmetry and says, "Oh, to hell with it."
Right.
Which is exactly what you shouldn't be doing.
Because they don't recognize it, right?
They don't recognize it,
Right.
exactly.
So and they don't know where to start, in fact.
Well, no, the first thing they do is to ruin the symmetry.
Right.
So you take something which is sort of invariant under a permutation group and say, oh, we don't need
So
to know
does
that.
this method, I mean, even at least for the zero-dimensional systems, work better than Grover bases?
So that's what but in fact, what Fourier did was he sort of did his Grosvenor basis now taking in consideration the symmetry.
Right.
So that was his paper from ISAC 2013.
So you're going to use this to apply to.
So what we do is just sort of describe the process in a much cleaner and different way. That's right.
Okay.
This sniffing out symmetries process, does it only work with zero-dimensional systems?
No, it doesn't seem to be. It just doesn't. I only know how it can be effective in zero-dimensional systems, but this sniffing out and finding it doesn't require a zero-dimensional system. Okay. Just requires playing with the exponents.
Well, since we really don't have much time, could you give a little hint on how it applies to differential equations? Or,
No, it's a legitimate dynamical system, something like that. So what happens is that at some level, don't forget, first of all, we're taking our variables dynamical system in terms of variables in x. We're changing it to variables in z.
Right.
no problem. You just get another dynamical system. Okay.
Right.
So now, how does the symmetry apply? Well, again, it's just a matter of rescaling things. So in fact, you can take this action and apply it to the dynamical system. You sort of say, okay, here's some variables. Now change the variables and do this action, where you can see what happens to the derivative of each component. Okay, you can see what happens there. You can see what happens to the right-hand side of a dynamical system. And so you can rewrite it in terms of an invariant dynamical system. And so that's no problem. What I can't figure out, for me, is what that buys you.
Well, you can certainly find the first integrals, right?
So I guess what happens is, so you can take this system, dynamical system, you can rewrite in terms of invariance, you can solve it if possible, and then work backwards, no question. I don't see, I didn't find anything that sort of says it looks simpler to solve. And so that was what, the part I didn't see. That's where I'm sort of stuck a little bit when I apply this to dynamic systems. When I did scaling, when Evelyn and I did scaling actions, in fact, it was a little different. There we reduced it to system. Quite often the polynomial system you have has less variables. And so when you take a dynamical system, all of a sudden you have less variables. And now you have a system which goes from like 4 variables down to 2 variables. You can solve the 2 variables system and then work backwards. And so we found some cases where, for example, we could solve it, Maple couldn't solve it, got a nice solution out of these things. But for finite groups, you start off with 4 variables, you still got 4 variables. So it should be simpler, but it's not so clear to me what it buys you. I mean, like for me, it's maybe a little bit inexperienced with dynamical systems, so I don't know if you've got a dynamical system, what do you do when you have a dynamical system? What do you do? What do you look for? I mean, is there certain diagrams that you're looking for, trying to emulate? And now if you have something that's invariant, and you look at invariant, and you look at the corresponding diagram, can that tell you something about the initial dynamic system? So this part I don't know. Is it numerics if you reduce it down to numerics, do you find a system that's better to solve numerically or has less problems? Again, I don't know, but that's lack of experience with dynamical systems.
The dynamical systems are discrete or continuous?
Continuous. But there's nothing that says it has to be continuous. Discrete would be just fine too. I mean, again, anything we can do is change the variables. Should be just fine, right? So that's no problem there. So interesting. So actually, I think I've probably run out of time. I do appreciate all the questions. I kind of had a lot of fun doing this lecture, and I don't think I'm going to ask for more questions at this stage. And so, okay, so let me thank you guys for coming. And,
More questions?
We just flash the rest of the.
Sure, okay. So what happens is if you actually,
minutes, right?
what you do is if you actually want to find the group, it's a matter of taking your input polynomials, looking at the exponents, at some level normalizing them so that there's always sort of somehow something that has degree 0 at the bottom, and taking the difference of the exponents. In this case here, these exponents are all 0, 0, and here's 3, 0, 0. Putting them into a matrix of exponents and trying to find sort of what's the matrix the kernel of. So now you're going to reverse the process. But that turns out to be no problem. You can take the Smith normal form of the matrix. Okay, which is just basically instead of the Hermite normal form, instead of triangulating, or instead of triangulating, you diagonalize the matrix. And the diagonalizing matrix is very special. It's ones for a while, and then all of a sudden some primes start showing up. Go ahead.
What's your favorite reference for normal forms of matrices?
Oh, I think in my own papers, but
You have a paper that just sort of lists all of them?
yeah, I'm trying to think of what's a good paper. I think if you just Google Hermite normal form and Smith normal form, you probably find some good references. Okay, it's probably pretty good. I mean, I say they're nice because I mean, the Smith normal form. Now you're trying to diagonalize, but diagonalize also where every entry sort of basically divides the next one. And so so these are basically the invariants, the matrix invariants, the determinant divisors, etc. So there's lots of ways to compute the Smith normal form. When you take the Smith normal form, you have to have the multipliers, the set of row operations, and the set of column operations, which diagonalize the matrix. Again, these must be invertible over the integers. You then take the set of row operations, partition it into an upper part and lower part, because the lower part is going to be the part that's the kernel. So now you're going to discover what matrix of exponents is this the kernel of? It's kind of this backwards question. And then, you know, the bottom part where there's some primes are going to give you the orders of where you're doing things. And then from that, you're going to be able to actually, from that, you're not only going to be able to sort of find the action, okay, the scaling action, which is going to be defined by A and P, the exponents in order, but you're going to actually also get the minimal generating invariance, the rewrite rule, all from that initial Smith normal form of the, so it's very mechanical, using, again, tools that, the minute you introduce the Hermite normal form, it's triangulating. So what's the next natural question is diagonalizing. So again, if a third-year student can understand that, they can understand Smith normal form too. Okay. And so from that, you generate everything you need to know. And here's sort of an example. Again, flashing through quickly, it's not so clear that that's going to be so useful, but we end up getting something very similar to it before. And the last slide was I wanted to discuss this. I want to extend this parameterizing dynamical systems. I want to extend the finite abelian to finite solvable group actions. That's, you know, interesting but not so doable, I find. And we want to combine scaling symmetry to finite diagonal actions, and we can do this by Smith normal form. We can do that.
So starting about the second item there, it seems like your plan for, oh, I see. What's hard is to find rational invariants for finite solvable.
Right. And actually, in fact, what happens is that, you take this problem, it's invariant under abelian action, so you modulo that action, but the fact is that the modulo set of equations you do are not sort of the necessarily, don't have a linear action by the smaller subgroup. So you don't have this sort of big group modulo thing, and so yeah, it doesn't sort of have the same sort of ladder structure.
So the problem is that the reduction changes linear things into nonlinear, and
Exactly.
the morphisms are nonlinear.
Exactly, it's exactly what's going on. That's right. And that's why it doesn't work.
So what if you have a finite abelian group of nonlinear morphisms?
Don't know. Right now, I don't have a single answer for that.
So in the example of the neural network,
Yeah.
you were using just a cyclic group,
Right.
and you got, I believe, 21 solutions, right?
31 solutions, right?
21
Yeah.
solutions.
But the whole system's got 31 solutions, or 21 solutions. 21.
21,
Yeah.
and you got all.
And we got them all in that case. Yes.
So you don't miss anything.
No, that's right. No, so we don't miss any. Matter of fact,
Even if you were able to do S3.
no, if we're doing S3, chances are we've taken the first system and reduced it down to a system where instead of finding 6 solutions, we'd end up finding 2 solutions or 3 solutions, and now take our order and then build the 18, and then we'd still have to do the non-toric zeros.
So when you look at these 21 solutions, do you discover any relations among them?
Well, you do, because it's orbits, right? Because you reduce down there, and then it's the same way as, say, if you take a matrix equation, reduce it to Hermite normal form, or reduce it to Jordan normal form, solve that system, and then what do you solve the thing? You take a similarity transform back to get sort of a parameterized solution of your initial one.
So you're
it's the
saying
same
that-
as what you have. It's the same type of.
So you're saying that the solutions could be partitioned in some way,
right?
orbits,
In orbits. That's exactly what's going on. That's right.
And
Yeah.
so
So that's handy. It's a nice structure.
So you're just looking for the generators of the orbits.
Basically, that's right. That's right.
Okay, all right. And in this example,
They had we had 6.
how many orbits are there? There are 6.
6 orbits. That's right.
6 orbits. And if you use S3, then there will be just 2 orbits.
3 orbits.
3 orbits.
Yes,
Okay,
yes, yes.
thank you. Yeah.
So somehow the theoretically interesting thing for you is finding the rational invariants.
Right.
And the application that you currently have is basically good for feasible solutions of actual nasty polynomial systems, where if you just feed the system to the computer algebras as they exist, the computer algebras go "Nope."
Yeah.
And
No, actually,
if you
no,
do this reduction, then it
yeah.
actually gives a solution.
So what happens is Fourier now takes advantage of if there's this finite abelian structure to improve on its Grobner basis. What we do, though, our advantage is we add a little more structure to the solution because they now can be described in terms of these orbits. And so I kind of like that. So we can do everything that, again, Fourier can do, and Fourier is the king of polynomial systems, right? So we can do what he does, but we also have this ability to now describe the solutions in a little bit more of a sort of interesting way, I think.
So what you're saying is that what Fourier was doing was returning the 21 solutions in a heap, and you return 21 solutions, remembering
A
how
little
they
bit more
stick
structure.
together.
Yeah, so I think that's sort of a way to do it. Okay.
Thanks again.
Again, thanks for the invite.